so much, Josefina, for the introduction. And thanks, Francesco, for coming on stage.
Great to be here.
And I think the idea that we had for this panel today is actually less talking about sort of the future of energy and sort of fusion, but how you actually get there, right? Because it's obviously a massive task you're obviously working on, and the question is sort of how can you actually make it happen? And I think what you, and this is sort of what we have sort of discovered in sort of the conversations we had with you, is that the way you approach it is in fact a blueprint for future engineering, and also the way how we can sort of make transformation in engineering and sort of in industrial sort of segments happen in Germany, but not and also in Europe. And I think this is sort of it's a fascinating way how you approach it. Also given that you have a fairly small team for the size of the task. So that's actually what we would like to discover today in this conversation. And you have brought sort of some slides with you. I mean, maybe you just walk us through them.
Yeah.
To make it a bit more tangible what you're actually doing and why it's so transformative and interesting.
Super. I'll get up to show the slides and give a little bit of an illustration for what we mean when we say that we are trying out a different kind of engineering process. So what we're doing at Proxima, as Christian mentioned, we're a relatively small team. By that we mean about 60 people between Munich, Zurich, and Oxford. And we're working on stellarators. You can think of these as stars that are put into a magnetic bottle, which looks like a donut with magnets. The thing you see on the left is an experiment that actually is already operating. It's in the north of Germany within the Max Planck Society that, as was said, Proxima spun out from. The thing on the right, instead, is something that we've been able to produce within 1 year of operation. The company has really just been running for 18 months, give or take. And that is a stellarator that can work as a power plant. And the fact that we were able to go from knowing about the Wendelstein-Siebenex experiment in the north of Germany to that is a result of the ability to iterate fast. So I'll try to give some feeling about how we're changing the way we design these large engineering systems. So as I said, this is not a theoretical topic at all. What you're seeing here is Wendelstein-Siebenex, or W7X for short. This is in Greifswald. It's a heck of a big machine. We're talking about heavy hardware. But what, as Christian was saying, what I was asked to discuss is more, how do we simplify it? How do we accelerate the iteration? How do we make this all come to life faster for the sake of clean energy? So to give you a feeling, let's see if this one works as a video. Yes, so these are many components. A stellarator is a complex beast, and therefore you have to think about how to bring together a plasma, which is hot ionized matter at 150 million degrees. You have to make it work with physical materials that are real. We're talking about real steel, real tungsten, and so on. And all of that needs to go with ways to capture the neutrons, ways to keep the magnets in cryogenic conditions, all these weirdly shaped structures. Those are superconducting magnets of a completely new generation. The ability to understand how these systems interact. If you do this with a classical engineering method, then you have the physicists sitting in one place, the engineers sitting in another place, and there are many kinds of engineering that come together in such a project. And then you lose more time thinking about system interfaces, so-called system engineering, then you actually are producing value. So this kind of design here, we're about to make an announcement in just a few weeks / 1 month. This was really the result of bringing together automation in the domain of design engineering across so many disciplines. To expand on that, something else that we can do once we don't look at just a few designs, but we start looking at hundreds of thousands of designs within a modern database system, is we start looking at different possibilities to actually not think about specific choices, but actually look at a continuum of solutions, which then we can morph between each other. So we stop looking at individual stellarator designs. What you're seeing here instead is a set of magnets with a plasma at the center, and these change into each other. So suddenly it's not a finite number of stellarators that we really have. We are training a device, a machine, to actually make the designs with us. Not necessarily for us. This still takes smart engineers that understand, that are domain experts in each of these things. But our job is becoming to actually design the systems that then can be automated. And for those that like the AI buzzword, there is a lot to say here as to how you can take these geometries of the plasma and try to sample how to find shapes that you couldn't find with the classical methods. Maybe I'll just leave this up here and we can talk more about how this also can really generalize to other kinds of engineering and how we think this can bring us to fusion energy much faster than people expect.
That's fascinating. Yeah, thank you for the introduction, Francesco. And I think this is, I think, you know, what we have to sort of realize. This is a super complex task you're working on, right? And you are a small team of 50, 60 people that have, within a year, worked on 600,000 different versions of this.
That's right. Stellarator.
Stellarator, yeah. Right? So, I mean, this is sort of, and I think this is the, and can you just maybe walk us through, you know, what's sort of so different in your engineering approach to the traditional engineering approach we typically know?
Yeah, I think it helps to understand where we came from in some sense. So we founded the company out of the Max Planck Society with also co-founders from MIT and from Google X in California. We came together in Munich as the starting point to work with the Max Planck Society, one of the key institutions in the world for stellarators. That device that you see here on your left is the most advanced stellarator on the planet by a large margin. Among the co-founders, Martin, one of my co-founders at Google X, he was leading a simulation team for drone deliveries, so swarms of robots, you could say. Before that, he was involved in the iterative design of Formula One in the McLaren racing team. Within the groups from the Max Planck Society and from MIT, we knew a bunch of things about both the physics and the engineering. So the perspective was we can actually think about designing fusion systems a bit like we iterate on Formula One racing cars. When you try to compete in Formula One, it turns out that you can't actually test the car on the track very often. You have to actually simulate it. This is part of the new rules, relatively new, in Formula One. So actually, the team that wins is, yes, the one that is best at hardware, but it's also the one that actually understands the product best and the one that can iterate the fastest. And you could argue that one of the key problems of fusion is that these systems are large, and therefore the iterative speed in building up the whole thing becomes pretty bad. And we need to actually be able to learn much faster. And if we can do it in simulation, that's great. The next bit of the thought is, okay, nice, sounds like you're good at programming, but do you know that your simulations actually meet reality? Well, if we didn't have W7X in the Max Planck Society, this would not be scientifically mature. But a lot of things have changed in 2022 when we brought that machine up and running. This is a 1 billion investment by the German government, something visionary that Germany has really done. That's why we're here.
Yeah, and basically, to summarize what you basically do here is it's a machine learning, simulation-driven engineering approach.
We talk a lot about simulation-driven engineering as a way to say we're looking for solutions that you can't find as a human. And it's all about the integration and about eliminating communication between humans, where oftentimes design conflicts arise, where lots of discussions arise, and we do like the humans, but we like actually the machines doing the work better.
And that's basically also the foundation to work on something that is so complex, like fusion energy, right? This is sort of
you could think of this as we are trying this kind of approach on arguably one of the hardest technology problems that humanity could tackle, and because without this kind of method, the horizon of fusion energy is far enough. Now we try to think about a different way of doing it so that we make it more realistic, but then it's a way of thinking. It's a way of actually designing systems much faster.
Yeah. So you mentioned Formula One and sort of and the similarities there. In theory, with your approach, you could build anything and construct anything, right?
Yeah, there are ideas in this design framework that actually come from Formula One. If you think about swarms of robots, you're forced to think. If you are trying companies that do deliveries or automatic driving, they are forced to actually simulate more than in large-scale manufacturing. Yeah. Now, when you look at a device like W7X, you're talking about big chunks of metal. And you might think that this has to be old-fashioned in some way and that it's all about forging and the material properties, and that is definitely the case. That is one of the great strengths of the German Mittelstand and other parts of Europe, but we can actually direct how we use that strength of our industry, especially in Europe, with better simulation systems.
And building on that, so you have obviously now sort of designed the stellarator, and now you have to basically build the hardware, right?
Mm-hmm.
Make the transition from the software to the hardware, and there I think your approach you have for basically building the hardware is, I think, also quite transformative. That you say, I'm actually not keen to build everything myself, but you're very much relying on networks, on existing infrastructures. Maybe you can help us understand that a little bit more.
It's one of the things that most people don't quite realize in magnetic confinement fusion, which means stellarators, but also the more conventional tokamak approach. The supply chain, the number of companies that can produce these parts is exquisitely European. We have simply done more of this in Europe compared to the US, compared to China. So that means we don't have to do things from scratch. And that's the value of public research. We don't have to reinvent the concept. We don't have to learn how to melt metal of a certain kind of, the special kinds that we need. Instead, we can work with Bilfinger, which is a large engineering company in Germany. We started working with them from day one on our magnets. We had just earlier this week in Greifswald, a German fusion industry forum, where we presented our latest designs, and we told the suppliers, come on this journey with us, because we're going to actually be the ones that are ready to direct. We are ready to do large-scale project management, but we don't need to do it alone. We don't need full vertical integration. We should think smart about how do we actually go faster.
And sort of, this is basically when there was a lot of discussion here at DLD around transformation of Europe. This approach is from this simulation-driven, machine learning-based engineering to then building the networks with existing infrastructures and production capabilities.
Mm-hmm.
That's basically the way we should think about transforming industrial economies, right?
We should think about what are our strengths. There is a fantastic manufacturing expertise in Germany. Recently, I heard that there are more people operating CNC machines in Germany than all of the United States. Yeah. These are obvious strengths that we have to use. At the same time, there are new tools. And so we should think about how do we actually win in this one. So there is no excuse for Europe to miss the ball on being the strongest continent for magnetic confinement fusion, because we have invested the most. Our American colleagues, friends, yesterday Bob was on the stage, was telling us about the fantastic things that Commonwealth Fusion Systems is doing in the US. We can do it in Europe on an approach that is better, and we can do it by leveraging our ecosystem much better.
And just maybe for the last sort of 3-4 minutes, coming back to sort of your company and Proxima. So how what are sort of the next steps for you? What is actually maybe sort of the missing part at the moment? And then sort of how close do you actually get, or are you already to the step where you can start producing energy?
Mm-hmm. So the drawing here on the right is a representation of a milestone that we have achieved, which is an integrated design of a stellarator for energy production. This is in peer review process with an academic journal. We care to show it publicly that this is now achieved. The next most important milestone is in 2027, demonstrating one of those magnets, these curvy shapes that you see in there. Those are some of the most powerful magnets humanity has ever made. We have to build one of those with our partners physically in the lab. That is the critical component. When we pull that off in 2027, then the next step is really going to build a net energy steady state fusion machine. That device is going to be actually smaller than W7X, about the same scale, really, but much more intense. The magnets will be at much higher magnetic field. We target that to operate it within 2031. That, depending on what kind of timescale you have in mind, is very short or very long. I think that's really basically like tomorrow. And then when we achieve that in 2031, the next step is going to build the first of a kind fusion power plant within the 2030s. When we have that in the second half of the 2030s, the 2040s needs to be the time when we actually go and build these systems for baseload energy, first in Europe and then everywhere else.
Fantastic, yeah. So I hope there's obviously enough support for you, both from private and public funding. Obviously, I think both the combination is what is important, and so that we can make a build a lighthouse technology here in Germany and in Europe.
Europe needs more of these, I think, projects that are not shy of going full out on the competition and building big things. Is something that most people are afraid of scale. When we talk about the energy system, scale is something a little bit mind-boggling, but we need to go after this because that scale we already have, we now need to be able to replace it, to make it clean energy, to add energy capacity. And this is one of the key opportunities, I think, of Europe.
And I think the encouraging thing is that we have access to everything that is actually needed to get there. Right?
We really have a shot.
At least from an engineering perspective and manufacturing perspective, as you elaborated. Francesco, thank you so much for coming, and best of luck with your next steps.